In this video, we're going to talk about collisions, which is the main question you will be applying this conservation of momentum principle that we learned about. And we're going to talk about when you can use energy and how that relates. So let's talk about the two main types of collisions. So first we have elastic collisions. In an elastic collision, the energy is conserved. So we have the kinetic energy, the change in kinetic energy will be equal to zero. So what will that look like? Let's say we have a ball traveling at each other. Let's moving some initial velocity. Let's say they're both moving the same velocity. After they collide and bounce off each other, they will still have that same initial velocity. So the velocity is conserved, and since velocity is within the energy will be conserved. And then also during this collision, the momentum will also be conserved. So the change in momentum will equal zero as well. Now let's contrast that to an inelastic collision. So an inelastic collision, the kinetic energy is not conserved. It does not equal zero. So if we look at a situation where that is, let's say two balls are moving at each other. Let's say one has a V1, one has a V2. And after they collide, they're moving at different velocities, right? We'll say 3 and 4. But they're going to be less velocity than initially, which means some energy has dissipated. And so energy cannot be created or destroyed, but it can be transferred. So it may be transferred to sound or heat or some other energy source, but the kinetic energy will not be conserved. And so if we have a collision where two objects are traveling at each other, and after they collide, they stick together and either have no velocity or some velocity, we call that a perfectly inelastic collision. But even with this collision, the momentum is still going to be conserved. So the change in momentum will still equal zero. Alright, let's look at an example where we apply these momentum and energy principles to a collision. So we have a ball at 25 kilogram ball traveling to the right at 10 meters per second collides with a 50 kilogram ball traveling to the left at 5 meters per second. If the first ball travels at 3 meters per second to the left after the collision, what is the velocity of the second ball? Okay. So let's first write out what we have. So we have the mass, and we'll call this ball 1, and we'll call this ball 2, just for our subscripts. So the mass 1 is 25 kilograms, and it's moving to the right at 10 meters per second, so the velocity initial is 10 meters per second. And so the direction does matter here, so we'll denote the right as positive, which is typical, and the left as negative. Okay, so then M2 is the mass of the second ball, which is 50 kilograms. And it's traveling to the left at 5 meters per second. So V2 initial is going to be 5 meters per second, but since it's to the left, we'll note this as a negative velocity. Okay, and then the first ball travels at 3 meters per second to the left after the collision. So we know that the velocity of one final is going to be 3 meters per second, but it's to the left, so that's also going to be negative. And we want to know what is the velocity final of the second ball. Okay, so when you're thinking about this, should we use momentum or should we use energy or something else? Well, we know that momentum is always conserved, and it doesn't tell us if this collision was elastic or inelastic. So it's always safe to use momentum when you have a collision problem like this. And since these velocities are constant, we can use that conservation of momentum. So we know that the momentum of the system initially will equal the momentum of the system final. And we'll define our system as the two balls. Okay? So we can write out our two momentums. So we have M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And it's very important to be clear about your subscripts because there's going to be a lot of different variables you're working with when you have a lot of different objects. So just make sure you're clear on objects 1, 2, 3, however many you have, and the initial and final for when things are changing. In this case, the mass is not changing, so we don't have to worry about having initial and final masses, but if they did change, you would want to worry about that. Okay, so we want to solve for V2 final. So this is what we want to solve for. So let's rearrange the equation to get that by itself. So we can say M2 V2 final equals M1 V1 initial plus M2 V2 initial minus M1 V1 final. Okay, and now all we have to do is divide by the mass, and we can get this equation with V2 final on its own. All of this over M2. Okay, so now we can just plug in our values and get this velocity too. So M1, which is 25, V1, which is 10, plus M2, which is 50, V2 initial, which is -5, because the direction does matter here, M1, which is 25, and V1 final, which is -3, all over M2. Want to be clear about which one it is. M2, which is 50. And so if we go ahead and plug all this in, we'll get a V2 final equal to 1.5 meters per second. And since it's positive, that means it's to the right, because we defined the right direction as positive. Okay, so I'll go ahead and box my answer here. But now you may be thinking, how do we know if this was elastic or inelastic? Well, we're actually able to check that, and that's what the next one is asking this. Was this collision elastic or inelastic? So, how can we tell? Well, we know if it's perfectly elastic, then the kinetic energy is going to be conserved. So we can actually check, does the kinetic energy change from initial to final? So let's go ahead and calculate the initial and final kinetic energies. So kinetic energy initial is equal to, obviously, the kinetic energy of ball 1 plus the kinetic energy of ball 2, which equals 1/2 M1 V0 1 squared plus 1/2 M2 V0 2 squared. And so we can go ahead and plug these in now. M1, which is 25, V0 1, which is 10, okay, M2, which is 50, V0 2, which is -5. And so notice that in this case we don't care about directions because the energy is a scalar quantity, and since it's a square, the direction will not affect it. So when we plug these in, we get initial kinetic energy of 1875 kilojoules. Okay, and let's do the same thing with final. So the K final will just equal the kinetic energy final of each ball. So we'll have the same beginning, but this V, we will want the final for V1 and the final for V2. Okay, V final 2. Okay. Okay, so we can go ahead and plug in our values here. So we have M1, which is 25, the V final one, which is a -3 squared plus 1/2. This is 50, and our V final 2, which is 1.5. That's what we calculated. And we get that this energy is only 168.8 about kilojoules. So this energy initial, does not equal the energy final, because we had 1875 does not equal 169 about. So we know that this must be an inelastic collision because this energy, or the kinetic energy, was not conserved. Alright, so make sure you leave your questions down below. This is the last for Unit 4, so make sure you stick around for next unit where we start talking about rotational motion. Thanks for watching.